Hi everybody, welcome to another video in differential equations, section 7.3, properties of Laplace transform. So we study more Laplace transform in this section. So first we have translation in S. So in particular what we mean by that is we transform from S to S minus A. So we will write S to S minus A. So in particular, what do we mean by that? So if we have a Laplace transform from the function of f into a function, a typo here obviously, Laplace transform from a function of t to a function of s. It says for when s greater than alpha, then e to the alpha t times ft is transformed, is a Laplace transform is going to be that. So first let's look at the proof, and then of course there will be a much better notation which help us do the problem a lot better. By the way, the formulas is over there on that side. So but first let's say we try to find the Laplace transform of this. Laplace transform of e to alpha t f of t. Now we still use the definition here. So that is the definition of Laplace transform. Just multiply the function by e to negative st, integral from 0 to infinity of variable t. Right. Now we have this, combine the exponents. Right. Then we can factor out the negative sign. Wait, that is not alpha, sorry, this is a. Yeah. It's no big deal. So we can factor out the negative, and we have s minus a t f of t dt. Right. Actually, that is the proof. They'll say, how do we go from here to there? Well, let's take a look. Look at this. In the definition, originally from here, let me write the definition for this one. If we just have the function, then the definition will go from 0 to infinity e to negative st dt, and of course we put a function there. Now let's pay attention on this one. If this is just s, then the function here just f of s. Now instead we have, here's the function, we have s minus a here, so the Laplace transform will be f of, instead of s, it's going to be s minus a. And that is the proof. Yeah, we don't even do any integral. Just notice that by definition, if we have an s there, the function is f of s. Now if we have s minus a, it's going to be s minus a. So we just have that. Simple enough. Right, so here's an example how we do this. However, the way we do this, of course the notation will be better, much better if we write like this. Laplace transform of e a t f of t. First, it's going to be the transform of the function f of t to f of s. But this e to the a t after we do the transform, we'll replace s to s minus a. That is the formula that I highly recommend that you use instead of this. Right. So we just transform the function. Just ignore e to the at completely. Just trying to transform the function. And whatever we have, replace s by s minus a, and a is the coefficient of t on the exponent. So let's find Laplace transform of this. So Laplace transform of this, first use this. This device will becomes that translation. And now we just do the transform of sine of bt. Sine of bt is here. And once we do that transform, replace s by s minus a, and that's what we. I will change the note before I post. Of course, in this table, if you roll down, we do have this. That's formula as well. Right, but focus on the transform in S and try to do it this way. Will be a lot better. Right, now we have a few examples here. So find the Laplace transform of e to the 3t times t to the 5th. Right. So first, we're going to have that device which transform s to s minus 3. Then we have t to the 5th. Now first we do the transform of t to the 5th. And what we have after that, replace s by s minus 3. Right, t to the 5th. Laplace transform for that. We use this one. Right, when n is equal to 5, so we have t to the 5th, or n is 5, so we have 5 factorial over s. N plus 1, n is 5 plus 1. Whatever we have, replace s by s minus 3. 5 factorial is 120 over, instead of s we have s minus 3, so we have s minus 3 to the 6. Right, by the way, this is for later. Math, go to numerical. Actually, the last tab, probability, that is the factorial. So 5 math factorial, or just 5 times 4 times 3 times 2 times 1. That's pretty much it. So simple enough. Next we have this. Once again, this device will transform s to s minus 2. So we first do the transform of cosine of 3t, and after that we replace s by s minus 2. Right. Cosine of 3t we'll use that. B in this case is 3, so we have s over s squared plus 3 squared, or s over s squared. I forgot to transform. So if s over s squared plus 9 transform s to s minus 2. I should say translate, because the transform is reserved for the Laplace transform. Right, so simple enough, right? Yeah. So we have this term. Just go ahead and find the Laplace transform of the the rest of them. Once we're done with the transform, when we have the function s, replace s by s minus the coefficient on the exponent, which is 1t, so which is s to s minus 1. So now transform of sine of 7t will be right above it. B, this case is 7. So I have 7 s square plus 7 square, and replace s to s minus 1. So in that case we have 7 over s minus 1 square. 7 square is 49. Yeah. So when we have the e to at, translate s to s minus a. So that's what we have. So simple enough, straightforward, right? Right, now Laplace transform of the derivatives. Now this is very important because after all, this is differential equation, so we're going to have derivative. So we need to know what is the transform of the derivative. So first, transform of the first derivative is going to be s times the transform minus the function s0. Right. The proof transform of the derivative is that. Now, the reason we write that from this step to this step, that is iteration by parts. Right. So iteration by parts. Let me write out integral udv equal. I need to slow down. Iteration by parts. Integral of u times dv is uv minus v du, right? So that is iteration by parts. So what are the parts here? So u e to negative st, that is u, and this is dv. So we have u v minus v well, the rest is difficult to say, but what's left is negative s, negative e to the st, and dt. Those are du. All of them together. Du. And so integration by parts, and we end up to that, and n goes to infinity if s is positive, so that goes to 0, and we just have f of 0 here and that function, right? So for higher order of derivative, so what do we have if we have higher order of derivative? If we have higher order derivative, we start from s to the n and only do the transform of the highest, only one term that go with the highest power of s, which is s to the n, and then decreasing the power. When we're decreasing the power from s to the n, we have f of 0, f prime 0, f. So the order of derivative increasing as the order of s, as the degree of s decreasing. Right. We'll see that in the next few examples, and we use a lot of that when we solve the differential equation. Because bottom line is we learn Laplace transform to help us solve the differential equations. Right. Now, so once again, if we have n derivative, we start with s to the n times the transform, and then s to the n minus 1 times the function, decreasing the order, decreasing the degrees of s and increasing the order of derivative of f. Now, use Laplace transform of the derivative of Laplace transform. Use Laplace transform of the derivative to derive the Laplace transform of cosine bt. Now, derivative of sine bt is b cosine bt. So cosine bt is 1 over b derivative of sine bt. So I will replace that into cosine bt. Now, just properties of Laplace transform derivative integral limit. Pretty much you can take the constant outside. That's what we have. Now, derivative of the limit. Laplace transform of the term with derivative. So first, on s times the transform and then minus the function when t equal to 0. Sine of 0 is equal to 0. So this one gone. And transform of bt, sine bt is this. And we have 1 over b and then s times the Laplace transform. Put all of that together. The b cancel out and we have that. So bottom line is we start with s raised to the order of derivative and then time the transform and then decreasing the power of s and increase the order derivative of the function evaluate to 0. So see how it works if we want to find the transform of the second derivative, which is initial conditions. So let's write out the formula. Laplace transform of the second derivative. This is the second derivative. So first thing we will have s to the second degree and then we have the transform of the function and then we just keep subtract s and then subtract s to the 0 power. So we have s squared, s to the 0 power, which is 1. And at the same time we're increasing the order of the function and the derivative. So original we have y of 0 and then we just have y increase the derivative. So s squared s to the 0 power and then we have to transform the function derivative, higher derivative, we just keep increasing like that. So if s squared, the transform of this is going to be y of s. We don't know the function, but we just write like that. The function is equal to 3 and the derivative is equal to 1. So that's what we want. That's what we have. Simple enough. So whatever the order of derivative, we start with that, s to that power, decreasing. And then the first one we have the transform, the second one we have the function, then derivative, second derivative, and increasing the order of derivative. Next, let f of x be that which is the transform of the function. I keep doing this. The function is in terms of t. Sorry. Once again, I will change that before I post the note online. You have the function in terms of t, little f in terms of t, and then the capital F is the transform is in terms of s. Right. So when we transform this, so now we have a different device. If the device is t to the n, what we do is we will turn that into -1 to the n power times the n derivative of the transform. Right, so what that means? So let's look at a couple of samples. Right. So when we have t to whatever the power is, that will give us, here we have t, right? T to the first power. So we just have 1. So according to that formula, we will have 10 to negative 1 raised to that power, and then we'll take the first derivative of the Laplace transform. Just the first derivative of the Laplace transform. What's left? Right. Yeah. So whatever t to that power, 10 to negative 1 raised to that power, which is 1, and then the same order of derivative of what's left. Right, sine 40 form is still there. We have negative 1 times, this is just the derivative. Derivative of sine 40, where b is equal to 4, b is equal to 4, so at b is 4 over s squared plus 4 squared. I have to take derivative of that. So give us negative derivative of 4 over s squared plus 16. Of course, the derivative. We can take the 4 outside. S squared plus 16. Now I can write s squared plus 16 to negative 1, and then take derivative using the power rule. Take down the negative 1, and then that to the negative 2, and then we have derivative of what's left, which will be derivative of what's left. Inside that happened to be x squared plus 16. Yeah. So just use the chain rule here. And so negative 4, negative 1, so that is 4. S squared plus 16 to negative 2. Derivative of this is 2s. Now multiply 2s and 4. Give us as s squared plus 16 to negative 2. So we have as s squared plus 16 will go to the bottom. The power is square. So that's what we have. Right. Next, we're going to do this in 2 different ways. Right, first, of course, we will use t squared, and then the second one we use e to the 3t. Right, so let's say right, let's just use what we just used here. Transform t squared e to the 3t. When we have the power of t, that will transform to negative 1 raised to the same power. And then we have the same order of derivative. Of not that function, but the transform of it. A negative 1 squared, just negative 1. Square is just 1. So just 1. So we don't even need that. So, and the transform of e to the 3t. Transform e to the 3t is 1 over s minus 3. 3 is a in this case. So we have 1 over s minus 3. And then this, we still have the second derivative. Right. I will rewrite this as s minus 3 to the negative 1 second derivative. Right, let's do one by one. First, I will take the derivative. It was negative s minus 3 to negative 2 times 1. And then we have one derivative. So that derivative one time, we have that. Take derivative one more time, we have 2. Negative 2, bring it down, become positive 2. S minus 3 to negative 3. And then we move that to the bottom. We have 2 over s minus 3 cubed. So that is one way to do that, using the transform of t in it. Next, now we're not using t squared. What we use is e to the 3t. And now this is the most important in this section. When we have that is the translation in s, meaning we just transform t squared. I mean what's left of the problem, and e to the 3t becomes the translation from s to s minus 3. So Laplace transform t squared, so we have n equal to 2 over there. So we have n is equal to 2, so 2 factorial over s to 2 plus 1, and transform from s to s minus 3. So we have 2 s cubed s to s minus 3, and that gives us 2 over s minus 3 squared, s minus 3 cubed, sorry. Yeah, of course we have the same thing. Well, that should be the same. So of course, actually this is not as important. This is not as important, but we definitely need to know when we multiply e to the 3t and we try to transform a function that has e to the something t, just transform what's left of the problem, and then s become s minus a when a is the coefficient of t in the exponent. Right. So what we need in this section, of course, is that. Of course, yeah, we need to know that too. But two things that we need to know is the transformation of derivative. Be able to do something like this, and of course, know how to transform where we have e to the at next to it. So it's rather straightforward. So make sure that you're familiar with the table, the Laplace transform, because you will need to use that when we take the test. So we don't have to use the definition of Laplace transform, which is too much. So we try to use the table. And once again, in this section, two important things. Transformation when we have e to the at is a factor, and then the transform of the derivative. With that, I stop the video here. As always, thank you for watching, and see you in another video in differential equations.